Hello and welcome back to the Calculus Fun Room. I want to talk to you today about derivatives and rates of change. So in a prior video, we have discussed the idea of an average rate of change and an instantaneous rate of change. We talked about those measurements in regards to an application. In particular, we would have looked at a rate of change like a speed or velocity, feet per second, meters per second. So in this video, I want to formalize that idea and make some connections to some things that we've already discussed. So visually, in the prior video, we would have drawn a graph, let's say something like this, and we have this generic function f of x. And we talked about how the slope between 2 points on that curve we called the secant line, right? So the slope of the secant line we had called the average rate of change when we were looking at some applications. So the way that we structured this idea initially was that we would consider having some point, let's say x1, y1 would be this point here, right? And then x2, y2 would be this point here. So what we talked about was the slope of any line, right, is rise over run. We have, delta y over delta x. So in terms of specific coordinates, right, we could write the slope in that manner. So again, the secant line is the average rate of change, and we would use really rise over run as a slope formula to do that. Now if you think about this for a moment, right, notationally, this y value here at x2 is x2. The y value is what we get from plugging into the function, right? So if we have the point x2, this y value is f at x2. And ditto for this guy, right? If we plug x1 into our function, the y value is f at x1. So we could rewrite this formula saying that this is f at x2 minus f at x1 over x2 minus x1. And again, whatever symbolism that we use there, we're discussing the same thing. We're discussing the slope of the secant line, which is also an average rate of change within any given application, like feet per second, miles per hour, that we discussed in that prior video. Now, we also discussed in that prior video, and we explored in a numerical manner initially, that if we wanted this average rate of change to become an instantaneous rate of change, what we in essence were doing, switch colors again, is we're looking at our curve, and what we're in essence doing is taking this point here and we're sliding it closer and closer. So again, we talked about that process of having this point approach this point. And in essence, what we were doing in that case is we were looking as the x2 gets closer to the x1, right? So if we had an average from, let's say, 3 to 5 seconds, then we looked at the average from 3 to 4 seconds, then 3 to 3.5, 3 to 3.1, 3 to 3.01, right? So we did that process numerically with some values in tables, right? So we're just discussing here conceptually again, we're letting x2 approach x1, and in essence, this point is getting closer to that point. And that was what we called the limit process, right? So we had discussed that the slope of the tangent was the instantaneous rate of change. I can't spell today. So we would have the slope of the tangent being the instantaneous rate of change. And I'm going to get lazy and abbreviate that ROC, right, for a rate of change. And that was the slope of our tangent lines, right? So technically that's a slope, and what it is it's the limit as right. Keep in mind the distance here we would call delta x, right? So we're letting the delta x distance go to 0 is what we're doing, right? So in our limit symbolism, so what I'm doing here is I'm looking back up at the delta y over delta x. We're talking about how the delta x goes to 0. Right? Or what we could do is in this symbolism, or more importantly, let's use this symbolism here, right? We are letting the x1 approach x2, or I said that backwards. We're letting the x2 approach x1. So I could say the limit as x2 approaches x1, where we have the change in the y values divided by the change in the x values. Right? My hands do not want to work today. All right, again, doesn't matter which of these symbolisms that we use. We're discussing the same thing that we discussed prior. An average rate of change is a slope of a secant line, and we would find the slope of a line in this manner. To have this average rate of change become instantaneous, we're sliding this point closer and closer to this point. So we're using a limit process to describe those points as they slide together. Now, when we also discussed in that video, we wrote a slightly different symbolic form, and this is really what we're going to focus on today. We're going to focus on more of a symbolic form here. All right, so another way to structure this concept, right? Let me redraw this exact same graph. Here's my function. So another way to structure this concept is here's our 2 points. And what we're going to do in this case is say we want the instantaneous rate of change at x equals a. So this is any number a. This could be x equals 1, this could be x equals 5. Heck, this could be x equals -3. Right, so we're picking some point x equals a, and we're going to move some distance away. Let's call that distance h. So we're going to call this the point a plus h. So our delta x, if you will, is this measurement h. So again, this ordered pair here is a plus h, f at a plus h, right? That's my ordered pair of that point, and then this is a, f at a. So if I take that same concept, right? So the slope of the tangent, right? The slope of the tangent, again, we're talking instantaneous rate of change, right? So I'm going to get lazy again. Instantaneous rate of change, right? So that's going to be the limit. And so in this case, right, when we look up here, right, when we look at the delta x going to 0, what we're discussing in this symbolism is this h distance is getting smaller and smaller. So the h is going to 0. So we have the limit as h goes to 0, and then again we have the rise, the difference in the y values. So here's our difference in our y values over the difference in the x values. And again, the difference between these x values is just that distance h. So here is a third way. Here's another way for us to describe the slope of a tangent using a limit process. We're just labeling the points differently. Now, in a section of a textbook at this particular point, we are formally writing the definition of what we call the derivative. This is supposed to be a here. We're formally writing what we call a derivative. So what we typically see symbolically is we're going to write this as f prime at a. So symbolically speaking, right, there's my derivative of my function. So in the past, we talked about an average rate of change, the slope of the secant line, becoming the instantaneous rate of change through this limit process. So even though we've had these prior conversations before, we're attaching the name derivative to this. So the slope of the tangent is the same thing as the instantaneous rate of change, and this is the same thing as the derivative, right? So the derivative of f at a, right, is symbolized, cannot write today, is symbolized as f prime at a. And again, it is the slope of the tangent, right, and the instantaneous rate of change. So the slope of the tangent is the instantaneous rate of change, which is the derivative of f at x equals a. Alright, so I paused the video for a minute to write some stuff down. I don't want you to have to watch me write it, right? So basically what we just did here is we defined the derivative. and we are making the connection that the derivative is the slope of the tangent line, which is the instantaneous rate of change. So symbolically, what we see here is that f prime at a, and that's how we read that, f prime at a is the derivative f at a, right? Derivative f evaluated at a. So f prime of a is the slope of the tangent line. So again, here's the slope of the secant line, f at a plus h minus f at a over h. But when we introduce the limit, that makes this average rate of change become instantaneous, becomes the slope of the tangent. And this is another way for us to write that definition. So these two definitions here, right, are for a derivative. We symbolize f prime. And again, this is really an instantaneous rate of change, which is also the slope of the tangent. So again, we're going to symbolize this derivative using the prime notation. Now, the reason that we're introducing this term derivative, right, is that rates of change can apply to many, many different applications in the scientific world. So let's say we are a biologist and we're studying the growth of a population of fruit flies, right? So we may be interested in how that population grows or declines. So we may be looking at, let's say, population per day or population per year. So there's our rate of change. We also might be a business person, and we're looking at the cost of manufacturing X units, right? So for example, we create bicycles. So we're looking at the cost of creating X bicycles, right? So we'd have, let's say, dollars per bike as our rate of change measurement. We might also look at, let's say, the national debt in the United States. We might be interested in how that debt is growing. And so we might measure the debt as a ratio of years, and we're looking at dollars per year. So these rates of change we see in many different science applications. We would see them in engineering, we would see them in biology and chemistry and business applications, so on and so forth. So again, in a physics scenario, we started this conversation in that last video using velocity or speed. We said miles per hour was our rate of change. We not only will see these rates of change in physics, but we'll see them in all those other science, engineering, biology, chemistry applications. Now, the rate of change we won't call a speed or velocity in those other applications. We'll have other names attached to them, but all of them are rates of change, and we want one word to attach to all of those measurements, and that is the derivative. So again, the purpose of this conversation here is to formalize the idea that a rate of change is applicable to many different fields, and that rate of change, that instantaneous rate of change, is what we are going to call a derivative. All right, so before we do an example looking at applications, I just want to come back and look visually. I love the visualization. I'm a visual learner. Everything makes sense to me when I look visually. So when we were talking about the average rate of change becoming instantaneous, remember what we were doing was we were plotting 2 points, and we were looking at the secant line crossing through these 2 points. Right? These 2 points slide closer together, and that becomes the tangent line. Now, Desmos.com, if you've never used this before, it's a really cool app built in. If I click, I don't think you can see this, but in the top left corner is 3 little dashes. There we go. And when I click that, it opens up these menus, and I've chosen the calculus of a secant line. Now, it gives you a predefined function, and I changed it to the parabola y equals x squared. And I just want to show visually, this is super cool. Right? I want the point of tangency to be at the origin, just for our visualization. And right here's the point of tangency, the a value. So I'm going to slide that to 0. Now here's me stepping some distance away. Right? So I'm moving some distance h, and here's the point on that graph. And as I slide that point closer and closer to the point of tangency, we can see the secant line become more and more and more of a tangent line there, right? So it's just really cool that we can kind of animate that, right? Let me slide my point of tangency here, and as I move those points closer and closer together, we can see that secant line become a tangent line. And again, let me animate that a little more. There's my secant line, which is my average rate of change. And then as we take the limit, that becomes a tangent line, which is the instantaneous rate of change. All right, so again, since we've discussed that visually, and we've made the definition of the derivative, all right, here's our definition. So when we've made that definition, we've talked about this being an instantaneous rate of change. When I mentioned that there's many different applications, let's take a look at a couple of those applications. All right, so let's take a look at an application. In this first application, I want to do something that involves physics, but then we'll take a look at another application that isn't physics, right? And let's take a look at instantaneous rate of change and slopes of tangents within this example. So pause the video just to write this problem down so you didn't have to watch me write it. So let's consider we are standing on a cliff that is 144 feet high, and we drop a rock. The equation that would describe the height of this rock would be negative 16t squared plus 144. And that models the rock after t seconds. Now in a physics class, we would talk about Newton's laws of motion, acceleration of gravity, and how to develop this equation. Actually, in fact, later in this Calc 1 course, we're going to also develop or derive that equation. But for the moment, let's just take the equation as given. Now, if we were to draw this graph on a calculator, a quick rough sketch of this graph, this is a parabola with a negative coefficient, so it points down, and then it shifts up 144 units. So roughly, let's say my parabola looks something like this. Now, we are at 144 feet when we release the object, and as time counts, right, this gives me, it's supposed to be an arrow there, right, this gives me the height of the function. So if this was, t equals 1, right, this point would give me the height of the function after 1 second. So let's do a couple different parts here, right? Let's say letter A, let's find the instantaneous velocity at, let's do 1 second, right, at t equals 1 second. So using our formulas that we just discussed, right, the velocity is going to be the derivative of the function at, in this case, at t equals 1. So we talked about this derivative, right, as our limit as h goes to 0. So we're going to have f at the a value, right, this was what we called our a value, f at a plus h minus f at a all over h. We're going to take a limit as h goes to 0 there. All right, so what we would typically do is, and we kind of talked about this in a prior video too where we discussed limits. So in order to evaluate this limit, what I'm going to do is a little bit of side work here. I'm just going to simplify this numerator. So let me pick a different color. Let's do a little bit of side work here. And let's simplify the numerator. So we're going to do f of 1 plus h separately. So again, I'm plugging this into my equation that I have, my height equation. So I'm plugging 1 plus h into my variable. So I got negative 16, 1 plus h squared, plus 144. And then I'm going to simplify this. Right? So if I square 1 plus h, I would FOIL. I get 1 squared plus 2 h plus h squared. Okay, so feel free to stop the video and FOIL that out, right? That would be the result that I would get. And then if I distribute here, I'm going to get negative 16, I'm going to get minus 32h, and then minus 16h squared plus 144. So the last thing I want to do here then is let's go ahead and combine like terms. So I'm going to rearrange in descending order. So I'm going to have negative 16h squared minus 32h, and then 144 minus 16 would give me 128. All right, now keep in mind if I look at my numerator, what I want to then do is subtract f at 1. So let me just rewrite over here in my side work what we're doing, right? We're doing f at 1 plus h minus f at 1. So here's my f at 1 plus h that we just simplified. Oops, I apologize, that's 32. Let me make that look a little cleaner. That is kind of sloppy. So we got negative 32h And then, where were we? Oh yeah, we're subtracting f at 1. So I'm going to plug 1 back into my original equation. Let me scroll up for a second. So remember, our original equation was negative 16t squared plus 144. So I'm going to plug t equals 1 into here. I'm going to get, negative 16 times 1 squared plus 144, right? And that is going to give me a value of 128. So here's the f at 1 plus h, and then I'm going to subtract f at 1, which is 128. So when I kind of clean all of this up and simplify this, let me switch to a different color, we can see that the 128s are going to cancel out. And what I'm going to end up with for the numerator of my derivative is negative 16h squared minus 32h. Right, so all of this is going to get plugged back into here, into our derivative formula. So the numerator of this derivative formula here is what we just ended up with, negative 16h squared minus 32h. So let me rewrite this. So I'm going to have f prime at 1 is going to be the limit as h goes to 0 of the negative 16h squared minus 32h all over h as h goes to 0. Now again, when we talked about limits earlier, what we talked about was direct substitution. So whatever our h value is approaching in this case, we would just plug it in. And notice in this case, if I plug h in the numerator, h in the denominator, I get something that appears to be undefined. So usually one of the algebraic tools we would use is we would factor. So we have an h in the numerator that is common, and I'm going to factor that out. And then we notice that the h and the numerator and denominator will reduce, right? They'll go away. So I'll get the limit as h goes to 0 of just negative 16h minus 32. Right? And then again, now I'll direct substitute. When I plug h in, I get 0, and I end up with negative 32 as the derivative. Right? Now again, we're interpreting the derivative as the instantaneous rate of change. Now if we think about our units on this problem, right, keep in mind our units are going to be the change in y over the change in x, right? So what are the units on my derivative here? Right, so the units are going to be, change in y over change in x, right? In this problem, the y units are the height in feet, right? And then the x units, right, are the time units in seconds. So we're getting feet per second as our velocity, right? Which we know velocities or speeds come in those units, feet per second, miles per hour, so on and so forth. So I'm going to do feet per second here as the unit. All right, so part B, let's say we want to find the equation of the tangent line at 1 second. All right, so remember that in order to find the equation of any line, what I like to do is use the point-slope formula. So what we need is the slope, and we already found the slope of the tangent line. Remember, the slope of the tangent line is the instantaneous rate of change, and in this case, that instantaneous rate of change was the velocity. So we have the slope, and then we need a point. Now we know the point is when t equals 1, and if we scroll back up and look at our problem, when we plugged 1 into our height equation, we got 128. So here's my x1, y1, and here is my slope. So I have y minus 128, and then I have negative 32. And I'm going to switch back to the t variable. Remember, that was technically our independent variable here was time. So I'm just going to switch back to that value. And then, so let me go ahead and distribute here. I'm going to have negative 32t, and then negative times a negative is positive 32. And then the 128 I'm going to add to the other side as well. So if I take 128 and I add 32, I get 160. So here is the equation of the tangent line. So what I want to do then is let's graph the equation of our height, right? Our height equation and our tangent line. Let's visualize what we have here. Alright, so again, I paused the video real quick and I plugged this into Desmos, and I adjusted my viewing window. My heights go from 0 to 144, so I did a viewing window of about 0 to 150. And remember, on Desmos, I can click in the upper right hand corner, I don't think you can see it, there's a shape of a wrench. Right, here's the wrench shape that I'm going to use to bring up the graphing window. So I did a Y min slightly negative, and then I did a Y min a little bigger than 144, and then I did an X min of like -2 something, and then a Y min of about 5. So it gives me a pretty nice viewing window here. And we can see that right at t equals 1, right, here's our tangent line. So here's the height function. Now keep in mind, in regards to the application, down here our x-axis is our time unit, right? So we're not really looking at negative time. This part of the graph isn't relevant to us. T equals 0 is where we begin, 144 feet off the ground on our cliff. And then as time progresses, we can see the rock travels in a parabolic path, and it's going to hit the ground right here. So it's hitting the ground at 3 seconds. And at t equals 1 second, we can see there's the point 128 that we had. And then here's the equation of our tangent line. Now remember, the slope of this tangent line being -32, that interpretation was the instantaneous rate of change, my instantaneous velocity. That was -32, right? That was the slope of our tangent line. So the 32 is telling me the speed, right? 32 feet per second is the speed. And then the negative shows that the rock is falling, right? So I have a direction heading down. Right, so again, let me scroll back up here for a second. -32 feet per second. So again, keep in mind, technically this is -32 over 1, right? So the -32 over 1, this says for every 1 second increase in time, I'm falling -32 feet. Right? So there's our visualization and our interpretation of instantaneous velocity. All right, now let's step back a moment here and let's discuss something a little more conceptual. So we used the formula to find the slope of the tangent at one particular time at t equals 1 second. Right, and we had used our formula for the derivative to do that, right? We said f at a plus h, and our a was 1 second, right? F at a plus h minus f at a. But what if I want to do this for any value of time, right? What if I want the slope of the tangent down here at 1.5 seconds, or 2 seconds, or 2.5? What if I want the velocity when it hits the ground, right? How quickly is it traveling when it strikes the ground? So how would we go about that process? Well, in other words, instead of plugging in 1 second, right, we're going to leave that value of time as arbitrary. And again, let me scroll here. Remember, that is this definition. So instead of plugging in 1 for the time, we're going to leave it as an arbitrary a value. So let's do a part C to this problem. All right, so part C, right, let's say we want to find the slope of the tangent at, let's say, t equals a seconds. Right? So in that case, we're going to have the limit as h goes to 0, right, of f of t plus h minus f of t all over h. So I'm going to do, again, in this particular example, we had -16 a plus h squared plus 144, right? So there's f at a plus h, and then I'm going to do minus f at a. So I'm going to have -16 a squared plus 144, right, all over h. So again, I'm going to do a little bit of side work. So let me come down here. I'm going to do a little bit of side work. I want to clean up that numerator. So I have -16. So a plus h squared is going to be a squared plus 2ah plus h squared, and then the plus 144. Right? And then I'm going to subtract. Let me go ahead and distribute. Negative times negative is a positive, 16a squared, and then minus 144. So let's continue to clean this up a little bit more, right? This is -16a squared if I distribute. -16 times 2 is -32ah, and then we get -16h squared. Again, plus 144. We had the plus 16a squared and the minus 144. And again, we're going to see the 144s cancel out. And in fact, in this case, we see positive 16a squared and negative 16a squared cancel. So what we end up with is negative 32AH minus 16H squared. So all of that goes into my numerator when I come back to my derivative, right? So that was all the numerator up here that I was simplifying. So I'm looking at the limit as h goes to 0, and we have in our numerator the negative 32AH minus 16H squared all over h. Again, just like we saw in part A, we're going to factor the h out in the numerator, and we're going to get negative 32a minus 16h all over h. The h's are going to cancel, and then I'm going to plug 0 into the h value. So after the h's cancel, I'm going to plug 0 into the h, so I'm going to end up with negative 32a. So this is the slope for every tangent line at any t equals a seconds. Now, if we think back to the first problem that we did, right, part A, we found the slope, right, at t equals 1 second, right? So we found the slope at t equals 1 second, right? So what we have here really is f prime at a is negative 32a, right? And again, this is for any value of a seconds in this problem. So we had f prime at 1 being negative 32 times 1, right? So we could find, right, we could say that the slope, right, at t equals 2 seconds is going to be f prime at 2. So in this case, negative 32 times 2 would be negative 64. And again, if we're talking about an application here, we're talking about negative 32, feet per second, or negative 64 feet per second. Again, we're interpreting the 32 and the 64 as being the speed, right? And then the negative as being the direction here. So again, just to kind of review here, right? The advantage of what we just did is we created the slope for this curve, right? We created the slope of every single tangent line. This equation, negative 32a, was the end result of the slope of the tangent. It's not just at t equals 1 second, it's for all values of t equals a seconds, right? So the advantage to that is we have a formula, and we could plug in multiple values of t very quickly. T equals 1, we could find the slope of that tangent, right, the instantaneous rate of change, our velocity. We could plug in t equals 2, right? We could find the slope of the tangent very quickly by plugging into my slope formula, if you will. All right, so this application, I paused the video for us to not have to watch me write anything on the board, right? So feel free to pause the video here for a moment and scribble this down on your notes. But in this problem, here's what we're going to take a look at. So we have a roast turkey that we're taking out of an oven when its temperature has reached 180 degrees Fahrenheit and placed on a table in a room where the temperature is 75 degrees Fahrenheit. Now, just so you know, if you don't do a whole lot of cooking, right, there's suggested temperatures that particular meats should reach to be safe. And a turkey, right, any poultry is suggested to reach 185 degrees. So that's why we're taking out of the oven at that temperature. And then I guess we're willing to pay the power bill to keep the room cold enough at 75 degrees Fahrenheit. So once we place the turkey on a table, it is going to cool to room temperature. So on this graph that we have over here, the blue graph is the temperature of our turkey. So it comes out of the oven at 185 degrees, and then it's going to cool down to the room temperature. So we can see in green here, here's the temperature of 75 degrees. So our temperature is going to approach room temperature over time, right, as it cools. So again, the graph shows this relationship as the temperature decreases. So what we're going to do, we're going to measure the slope of the tangent. And this is going to give us the rate of change of the temperature. And let's take a look at 1 hour. So what is that rate of change of temperature at 1 hour? And we're asking what are the units of this rate of change. And you can see on this graph that we've already been provided the point of tangency. So here's 1 hour, 60 minutes later, right? So here's 1 hour, and then we're drawing the tangent line, right? We're going to estimate the slope of that tangent line because the slope of that tangent line is the derivative of that temperature graph, which is our rate of change of temperature over time, right? So if we take a look, let's say we're looking at the slope of the tangent. That's how I'm going to write this, right? And again, what we're going to do in this case is this is kind of an approximation. So we know one point on the graph is, let's say, it looks like after 60 minutes, looks like the point is about 125. So we have one point here, we have 60 minutes and 125 degrees Fahrenheit, and then it kind of looks like at 30 minutes it might cross through this point here, roughly, let's say 150. Roughly, all right, we're estimating here, right? So let's say 30, we're at 150. So we're finding the slope between those 2 points, and that's going to estimate the slope of this tangent line at point P, right? So we're going to do 150 minus 125 over 30 minus 60. So again, I do change in y, 150 minus 125 over 30 minus 60. There's my delta y over delta x, my rise over run. So if we simplify this, we're going to end up getting negative 5/6 as our slope. So again, the negative shows me the temperature is decreasing. This is the rate of decrease, if you will. And remember, the units are y's over x's. So the y's is my temperature in degrees Fahrenheit, and the x's, if you will, is the time in minutes. So what we're looking at then, right, the interpretation of this tangent line is that we're cooling. So basically we could look at this two ways, right? We could say for every 6 minutes increase in time, we're experiencing a 5-degree Fahrenheit decrease in temperature, right? If we're going to write a sentence description, interpretation of this, we could say that. Right? And I'll go ahead and just get a decimal value for this. So 5 divided by 6 is 0.83, right? So this is about negative 0.83, and I'm going to say degrees Fahrenheit per minute. And so again, in that prior problem that we looked at, our rate of change was a velocity, right, a feet per second. And this application that we're looking at, our rate of change is temperature over time, so degrees Fahrenheit per minute. All right, so this finishes our conversation about rates of change and derivatives, and our applications of those rates of change, derivatives, and slopes of tangent lines. In the next video, what we're going to do is formalize this conversation a little more general, and we're going to talk about a derivative as a function of x. I look forward to seeing you next time.